Um, so we talked about, last time we talked about differential forms, just another angle. So it's the same business as derivatives and integrals. And so they're not going anywhere, but just reinterpretation of the integrals and derivatives. So derivatives can be interpreted now as fractions, okay? And integrals are now interpreted as if there is actual multiplication there. So that sign u du is actual multiplication sign in there. Okay, so that allows us to be more flexible. I think it explains a lot about integration. So, all right, okay. So the next topic is one of the more challenging ones: the solution sets of ordinary differential equations. Okay, so let's review where we are, where we have been. So a real life phenomenon. You start with a model, which is to begin with a verbal description of what's going on. And then you try to introduce variables, you introduce relation between them, and then maybe it is about differences. No guarantee that that's the way it works out, but that's what the calculus works. Is that the dynamics is what's being discovered, what is being modeled, and so the difference between two consecutive states, which would be quantities, location, and so on, somehow depend on where you are and when things happen. Okay, so that's equates your state as a sequence, and its difference, its dynamics, its differences, and then you just if the equation is very straightforward, in that respect, there is no trouble whatsoever to produce that recursive solution. So it is a solution, not just some consultation, so speculation like this, and then plus something h. Okay, that's pretty much what a recursive solution is. It is a solution, but it is not a continuous. And if your phenomenon is a continuous phenomenon, then that's not. It's not just an approximation. Okay. So that's how we started. Then we take, in the spirit of calculus, we take that limit, right? This limit, delta t, that's the delta t I'm talking about, and it goes to zero. Then this disappears. Okay, then you cannot have this. Once this h, let me put delta t there. Once delta t goes to zero, this doesn't exist anymore. There is no such thing as the next real value, real number. Right? So only for integers it works. So this is gone, unfortunately. And so we pretty much have to start from scratch. Even though you can hope that if you solve these equations, then you take the limit of their conversion onto the continuous solution, and it might be true sometimes, but it's really not very productive. So we start from scratch and assume that we already have that difference equation turns to a differential equation, which is an equation of derivatives. The derivative depends on the derivative of your quantity as a velocity, how it's changing, depends on where you are. Okay, so if you're unlucky, they try to solve it, but that's only when you're lucky. So then you can have an exact solution. We have a couple of times last time. Remember, it is for motion, it's quadratic. For free fall, it's quadratic. For population or temperature, it's exponential. But also typically you are not lucky, then you go back to different equations, and then you are dealing with the incremental solution. Once again, how it is related to the that continuous behavior maybe is not clear yet. But right now we assume that we're neither lucky nor unlucky here. What we're just trying to do is go theoretical and figure out what it means to solve a differential equation and what is the solutions look like. Okay, so to be clear, they have to be functions, right? So in the case of incremental change, it's a sequence. Now it's a function defined on the possibly infinite intervals. To understand it better, let's go way back to what it means to solve an equation, not a differential equation, but an equation. Okay, so x squared is equal to 1. That's an equation that you solve. You solve it for x, a number. So this is the algebra that we're used to. And now differential equations will be solutions of functions. And one thing to be very clear about it, the solution of the set. So it's never one. So there is no such thing as a solution. Well, there is such a thing, but really at the end of the day, we want all of them, right? So one solution x equal 1 is a little good here. Okay, so as an example here is a couple. So 2x is equal to 4. Solution set is written like this, and it is 2. Okay, so remember the set building notation, everyone. Okay, so x in this case it's a number. Okay, so a real number. Okay, and then it satisfies the restriction. 2x is equal to 4. Simplify, and the answer is 2. So it consists of one single number. If you go with x squared equal to 1, solution set is written in an implicit way like this, and then it's simplified, and then you have your simple answer. That's what to solve it means to produce set in the simple form that is actually is listed ideally. X squared is equal to -1. Among real numbers, there is no such thing, so it's empty. Okay, this one is another extreme situation. X minus x equal to 0. Every x satisfies it, so every number is a solution. Okay, so if it is this complicated, the solution sets are this complicated among numbers, then you can imagine that among functions it will be even more complicated. But at least these are the main possibilities: is 0, 0 solutions, 1, 2, and infinitely many. All of these are possible. So a quadratic equation. So there are some. Let's take a look at some indirect. So in the spirit of this particular topic, it's not this, not specific. Some theoretical answers can be given without examining the actual situation of the equation, such as a quadratic equation has 2, 1, or 0 solutions, depending on whether the discriminant is positive, 0, or negative. Does it sound familiar? So the point being, whether you have or do not have, the point here is no quadratic formula. Okay, so if, for example, if you don't remember the quadratic formula, or maybe it doesn't exist, and somehow, this is still true. Okay, so it's the classification of the quadratic equation into 3 categories: 1 solution, 2 solutions, 0 solutions, which corresponds to what does it mean about does it tell you about the graph? The graph of a quadratic equation. Okay, imagine the graph of a quadratic function rather, and then there are possibly various number of solutions depending on where the graph is located. So, what does the graph look like for quadratic function? A parabola. Okay, so what is the solution to quadratic equation relative to that parabola? Okay, so I drew it without the axes. Okay, so depending on where the axis is, what?
How many zeros you'll have?
Right. So can you envision what it looks like? So geometrically speaking, what does it mean? Where are the solutions? They're not here. Where are they? How do I visualize the solutions?
You draw in the x-axis.
You draw the x-axis, and then depends on where I draw it, right? So because the solutions are the x-intercepts, so I could draw it here, no solution. I could have draw it here, 1 solution, and 2 solutions, right? 2, 1, 0. Okay, so that's how we classify quadratic equations, even though we don't have a formula. We know that the graph is a parabola, even though it doesn't have to be a parabola. We just know it looks like this. We don't really know what parabola is, but if we know it looks like this, then depending on where it is located relative to the x-axis, we know how many solutions it will have. Okay, so very general statement. without actually finding them because we don't have a formula. But it is informative. It's very good to know, and we'll use that situation more often than the quadratic formula itself. Okay, so that's one example. Another example of of the idea that's coming up is at the bottom, a cubic equation always has a solution. Have you heard this idea before?
Yeah.
Why does the cubic equation always have a solution?
First example I can think of is like a square root of like a -8, or like square root of a negative, or not square root, a cube root of a negative number.
Right. So which means that you'll never encounter what you're trying to say here is this is a no. So not for cubic. So you cannot miss a cubic graph with a horizontal line. So you ask the same question, where does the cubic graph lie relative to the x-axis? And what you're saying is that you cannot miss it. Okay, so indeed it is true, but there is a more general statement, and then I hope you can remember where it comes from right there. There exists a solution for every equation f of x equal to 0 with a continuous function that takes opposite sign at the end of an interval. So on one side it is the interval, so this is the domain. Okay, on one side it's negative, on the other it's positive. Okay, and then what we're saying here is that there will always be a solution, meaning an x-intercept. So you see the picture, you have the picture in your mind. Positive on one side and negative on the other. So this is the x-axis, and then this is the domain. Okay, on one hand it is negative, on the other hand it's positive. Okay, so you see what we're saying here. Can you put it in words? Graphically speaking,
In order to get from one spot to the other, you have to.
you have to cross the x-axis, and the reason is because the function is continuous. Okay, so if it was not continuous, was not required to be continuous, then you can just jump. And there are no x-intercepts, there are no solutions because the function is continuous, it has to cross. So that idea of continuity is maybe kind of a secondary in calculus. It's in certain contexts, it become more and more important. So this is one of them. And so when the existence of solution is then guaranteed by the continuity of the function, there is a theorem that, remember the theorem for calculus 1 that says roughly this. Or if, the function does not miss values, continuous function does not miss values. So this is the lowest, this is the highest, it will not skip any. What is it called, that theorem?
Is it the fundamental theorem?
No, fundamental is about derivative and integral and how they connect to each other with this matter. No, there's another one.
Intermediate value.
Intermediate value theorem, right? Yes, intermediate value theorem. So no, so there's two values, the highest and lower. Between them, intermediate values are not missed. They always will be covered by the function, and that's what guarantees our conclusion about the existence of the solutions. So the continuity will come up again at this point quite a bit. At this point, the point is what we're able to say about the solution set of our differential equation without actually solving it because it's so hard to solve. Okay, so these are three ideas are just to suggest that something like that we've seen before, so we can say something about solving equations without actually solving it. Okay, so a solution is any number. So once again, we use the analogy between numbers, equations of the numbers and equations of functions. And so this is number 1 is x equal to 1 is a solution because when we plug it in, we have the correct true statement right here. Okay, 1 squared is equal to 1, but it's to find all solutions, which then speak of the solution or this solution set, because then you have to include both 1 and -1. And so 1 is not the solution, but it is a solution. And then the only way to resolve it is to to speak of this solution set as well as of all the solutions. Okay, so so how to find the solution set, we're not concerned right now, just what it's supposed to look like. It's kind of important, but also not entirely new. Okay, so that's an example. So how this is a differential equation. So the derivative f prime of t is equal to t. We can actually solve it for a change. Okay, t squared over 2 is a solution. Okay, so just nothing but integration. So this is nothing but integration right here. So but ignoring that it's solved by integration, what does it mean to solve it? You can plug it in back and confirm that it's true. So what is true? Unlike over here, this is equation of numbers. Okay, this is equation of functions right here, equation of functions. Okay, so then what does it mean for two functions to be equal to each other? They may have different representations, but they're the same, just like 1 plus 1 is equal to 1, I'm sorry, 2, these two functions are, two numbers are equal to each other, even though they have different forms. In fact, complicated things, how about this? Okay, so here I can also have this. Okay, so functions in the first line is equation of numbers, in the last one of functions, and the y are they equal to each other because no matter what x is, it's still true. Okay, so the second line is the quality of function. So that's when we then to plug in into the equation, unlike over there at the top, we have to actually confirm that either it's exactly the same formula, okay, then we're in luck, or we have to demonstrate that no matter what x you're going to plug it into it, you have the same answer. So indeed, if I take t squared over 2, I differentiate it, and so I have f prime is equal to 1/2 2t, and which is equal to t, and it checks out. Okay, so that's how we do it. And we also know that we have not found all the solutions, right? Just like with the second equation, also this one cannot be solved by integration, but we just know the answer. Right, so if you have derivative is equal to the function itself, it's the exponential function would be a solution. And once again, you can plug it in and demonstrate that at prime is equal to et prime is equal to et. So they're equal to each other. Two functions on the left and on the right are the same, and so that's how you know the two functions are equal to each other. Once you decided what f is, so f is the name of the function that we're looking for. Okay, to be clear. So over here, x, everything rotates around x. Over here, that's my, I'm sorry, no, this one. This is my equation, and everything is about x. Okay, and here, everything is about f. And so once we speak of function, we can do algebra with them, just like before, but we can also do calculus. So in this case, derivative. These are order 1 derivatives, but you can also do order 2 derivatives to do. When do we need second derivative? Second derivative? What's the purpose might be in real life phenomena?
Acceleration.
Acceleration. Okay, so if we move, so we have to move, we're doing the order 1. So we're not even doing anything like free fall really because that would require second derivative. So a little bit later. Okay, so okay. Okay, so just like with the solving equations, the word problem is translated into problem of unknown variables that we name. Okay, so similarly here, what we have done a few times, we name the variables, but also the function itself. Okay, however, it is actually a convention in differential equations, which differs from calculus. No name of the function. Okay, so that f that I use right here is actually frequently is not commonly used. Okay, so because there are many derivatives, many variables, it is just becomes too cumbersome, and instead we rely frequently on the Leibniz notation, and we speak of the derivative of the variable. So y is a function of t, but there is no name of the function. Y is the output variable. Nonetheless, nonetheless, we just say that that's what y is. So simultaneously the output variable as well as the name of the function, okay, whichever you prefer. So you can write, then you're allowed to both write y prime on one hand, that would be Lagrange notation, but also this one. Also very convenient because that reminds you that this is a fraction. Okay, so then I'm taking these equations that written with respect to f, and then the independent variable t is divisible. Okay, so let's rewrite it in the spirit of the theory of differential equation. That's what it looks like. Y prime is equal to t. Okay, so then you should guess that y is the dependent variable, t is the independent variable, and y is differentiated with respect to the only one other variable that we've got. So y prime is equal to t, and then solved.
Wouldn't dy dx be meaningless if y is only a function of t?
I'm sorry, this is the. Okay, so I just took it and rewrote the first equation. I don't think I did this right. So this is calculus. This is in the calculus spirit, and this is in the differential equation spirit. Okay, so it looks quite a bit different. So I hope you'll get used to it. So you just see it in certain places, and then which is kind of cumbersome when you do it in calculus. You have to this notation. Then there are like 3 types of notations that are in why we pick one, or we only need one, and so forth. But as you can see, it's just a matter of tradition and customs to use these variables and not names of functions. Because when it is actually one what you're looking for, it makes sense to give it a variable that is the name of that looks like a variable. So one here is a function that will, and it's more compact. Okay, so this is what the substitution looks like. Y prime, I substitute t over t squared over 2. I differentiate, I get t. Okay, then I e to et, I substitute, I differentiate. Once again, it checks out. Okay, so the row on the left, the right hand side is on the right, and then at some point where the question of emerges is this one. And so I ask, are they equal to each other? And I say yes, they are. And so I confirm that these are solutions. Okay. So more generally speaking, that's what we can write it. If you want to make t explicit, then you have these parentheses, and we just at some point we'll just fade away, and we'll just assume that there's a variable there, independent variable. We don't want to repeat those parentheses all the time. Okay, so that's you can speak of as if it is location independent. Once again, t time always, and then just for convenience, y is the location, even though it could be any quantity that is changing. So 2 main clauses are when the dependence is the right hand side of a differential equation does not depend on where, so it's a location independent. And they're like the number 1 over there. Okay, so the solution is nothing but integration, but let's make it just to make sure that it's nothing but a small part of this big puzzle, small piece of this puzzle. So let's examine it from the point of view of differential equation. What does it mean? So we examine this differential equation. So once again, y prime is equal. I don't want to write this, right? This one would be confusing because that function g doesn't depend on what do we have here. It doesn't depend on t only or y only or both. Okay, and that's we have to deal with both situations, and so but this time let's say g depends on t. So what does it mean to solve this differential equation? It comes from what we did those experimentations, numerical simulations in the beginning. Remember, so we are progressing from left to right. So the horizontal axis is time here. Okay, time t. Okay, and then the right hand side is what does it give you? It gives you the slope of the function that we don't know. Okay, so that's what makes it the problem that is somewhat manageable is that there are a bunch of slopes, and that's what the equation gives you the slope. So depending on the value of g, let me zoom in. Okay, depending on the value of g, you draw a slope just as we did before. So for example, g of 1 is equal to 1, so the slopes are 1. Then it is 0, so they are 0, so the slopes are 0. So we're just visualizing g, not trying to solve it yet. And g of 3 is equal to -1 going down. Okay, and then it's -2 down, -1 down, 45 degrees, -2 is steeper and steeper. And so in that way, we have the whole field prepared for what? for a path supposed to go through this field of slopes. And each slope is its foot. Curve will go through, and the slopes guide our curve in what way? These are the directions which way the graph is supposed to go, but certainly you don't know where you're going to be crossing. So the point is that these are the slopes, and so therefore they're the tangents of my curve. The curve that I'm looking for will be touching each of these slopes. So I don't know what it's gonna look like, but it might look like this here, and over here it will look like this, or maybe like that, I don't know. But these are the requirements that spelled out in my equation. Okay, so when it is, if we leave it as this, then without intermediate values, and every single vertical line has these slopes, then we could do what we did before. Okay, so just follow those slopes and jump to the next location, look up the slope there, jump again, and on, and we have a sequence of locations which solves the problem incrementally with a recursive formula. Okay, so we are not doing that anymore. So we're trying to solve the problem that actually is not about differences, but about derivatives. And the challenge is dramatic because there's no next stage. You don't jump. You're supposed to move continuously and change the direction continuously. Okay, so all right, so we know how to solve it. Okay, so just to refresh your memory, because it is solved by integration, you can do it literally. Do I have it here? You can do it literally, right? So if I integrate integral y prime dt is equal to integral ft dt. Okay, on the right, on the left, there is a cancellation. What do I get? Differentiation followed by integration. Just y, and here I have the integral, which is now to be evaluated when tf is specific, and we solve the problem, so that to that degree we say it's solved. Okay, so and then the plus c over here comes up. Why so? We know that that's the kind of a ritualistic step that we make. We solve the problem, and then by integration, and then at the end we write plus c. You can see the geometry suggests why. Can you see why how geometry suggests that is the c will be indeed. Well, what's the meaning of plus c?
Constant.
It is a constant geometrically speaking. What do you see if I start plotting more equations, more solutions?
Go up or down.
They will be intact, right? So they will be shifted vertically in the same way, because as you can see, those slopes, look at the slopes, they change in the vertical direction, but they're changing in the horizontal direction. In the vertical, they are not. So over here, if alternatively to what I have here, I start here, I will end up with the same shape as the green one is the same as the red one, except shifted in the vertical direction, because that's what the slopes are like. So if it won't have one, you have the rest. Naturally, that's the incremental solution. Here it is something more subtle, but not really by far subtle. Why it's the same? Because differentiation, it's the same derivative. Okay, so that's why they produce the same derivative. There is a whole theorem about it. Not only every plus c will produce the same derivative, but also conversely, if you found another antiderivative that it has the same shape plus c. So as long as there are no gaps in the domain, we are okay. So that's the picture you should have keep in mind. Okay, so an integral. This is my differential equation right here, and I'm maybe not written. No. So f uppercase is what I'm trying to solve here, and the solutions, they are numerous. They have the same exact shape, and if you have one, you have all. So find one, find all, right? So that's the point. That's what makes calculus 1, 2 is still manageable. And so that's not going to be as easy anymore. But in this case, that's the idea. And so what we end up with is we say a family of solutions. Why so? Because they're not random. They're connected to each other in a non-random fashion. They're closely related to each other, really close. And so because of the shift, the shape is exactly the same. But also what's important is there will be, these are the two important things. These graphs cover the whole region, but do not intersect each other. Okay. So so these are why are these two important? So why do we pay attention to that? Because, well, try thinking in terms of any practical problem that we let's say motion. Motion is described somehow through differential equation, and then we try to find all the solution set like this. And then these two properties are important because what if they were not satisfied? Without the first property, the model doesn't cover all possible situations. Situation meaning initial conditions. So for example, at this moment of time, I'm starting at that location. I'm supposed to follow the dynamic that describes the differential equation and produce a solution. So if there's a missing, if this curve does not, no curve covers that point, then there's no solution. So that's not good. There's something wrong with your model. Or for the second one, they don't intersect each other. Why is it bad? The two curves intersecting each other. Why is it bad?
Correct antiderivative.
No. Once again, imagine that you have a particular dynamics described by the differential equation, okay? And then what we're saying here is, what if there are two curves that are crossing each other, and then somehow, at the point of intersection, we're trying to predict the future. That's the point of the model, right? And if there are two curves, then what?
Hard to choose which one.
Not impossible, right? So if both of them are truly solutions, then we are unable to choose one over the other, right? So then there is no prediction. Then the future is ambiguous, and so either future is ambiguous, in some certain sense of maybe randomness there or something like that, or our model is not deterministic anymore. So that's we don't want to go in that direction. So we're trying to keep the things under control, as if what we're doing is something like motion of planets. So planets don't do this. So the planet is here and it goes one trajectory. It will not go in two directions at the same time. So that definitely we do not want that to happen. So these two properties then will go on for forever as the requirements of what model we want to have. We want to have these two properties. We very nicely visualized by this picture, but that does not have to be as simple. Okay, so let's take a few examples of when we do not look at differential equations or integration, anything like that, and just look at what families of functions might look like that satisfy these two properties. A bunch of parabolas shifted vertically. Okay, so, well, there you go. Y is equal, in this particular case, y is equal to -1/2 t squared plus c, so vertical shift. Okay, it's a one parameter family of functions. That's the observation that we make. One parameter referring to c. C is the parameter. For each c, there is a curve. Okay, and once again, they do not. They tight to each other just like a book. A book right here, but you can imagine pages of a book. They're like this. Okay, so they certainly cannot intersect each other, and it is the book is solid, right? So if you don't separate pages, it's like a piece of wood. Okay, so that's the solution set. There's no solution set. That's a family, and I'm using the set building notation, but not for numbers, not for anything else, but for functions. Okay, so I have a bunch of quadratic functions here, and they are visualized here. For each c, we have a separate one, and once again, we can easily demonstrate that they do not intersect. So let's they do not intersect. That's number two. And number one, that is fully covered by the curves. So the picture certainly is suggestive. even though not every one of them is plotted, but it's suggestive that it's not missing any of the points if we are, oh, we can do that. So let's make some very simple computation and confirm that. Okay, so we're not doing differential equations at this moment. All we have, what we have available is this collection of functions, one for each c, and then what I want to demonstrate is now property number one, the plane is fully covered by the curves, and then the second one. Okay, so once again, if why it's important, if these curves represent the following objects, we want to have any initial or final conditions is possible. Okay, so we cover all possibilities. Final position. So if I'm throwing from this position in this under this angle, we should be able to trace the ball. Or I'm trying to hit the spot over there, so I should be trace it backwards and be able to hit that spot over there. Okay, and there is only one path for every initial condition, initial position. Okay, so let's prove these statements without referring to differential equations, because the differential equation, whatever it was, has been solved. Okay, so for the plane is fully covered by the curves is translated as it is the union of the curves. Okay, the union of the curves, and so in other words, every point on the plane belongs to one of the curves. Okay, so let's solve it. Let's solve it. So this is what we're talking about. There's a point T naught Y naught on our. I have my TY plane. T naught Y naught is an arbitrary point that we chose out of the bag. And then we're supposed to find a curve for it. That's what it means to solve, to demonstrate that there is a curve for it. Not too complicated, okay? Because this is the condition that the equation that we have, and it passes through point T naught Y naught, which means that then we plug in T naught Y naught into my equation. It's supposed to produce a true statement. So this is true. It's a relation between the 2 quantities. That's a given, once again, it's a given. Okay, so then what is that we're after? We need to find a specific C that would satisfy this property. Can we find C that satisfies this property? Yeah, so that's right. So didn't mean to be a trick question. So for C, and that's it. So if you have T naught and Y naught, like in that picture, the C is right there, it's given for you. Okay, just solve this equation and you have a C. So indeed, every point, no matter what T naught is, Y naught is, there's a curve passing through it. Therefore, the whole plane is covered by these curves. Okay, so on the second one, the second problem, the curves don't intersect. Entirely different issue, by the way. So two curves that intersect are the same curve. That's another way to put it. So once again, there's a point, T naught, Y naught, and then we imagine that there are two curves passing through it. We have to demonstrate that that picture on the right is impossible. Okay, so once again, this is given, an arbitrary point. We're dealing with all points at the same time. Okay, and then we have to demonstrate that they cannot intersect. That's in a mathematical, in a logical twist. It's the same as to say that if two curves do intersect, it's the same curve. Okay, so once again, there are 2 points, and there are two curves rather. Okay, with C and with K, that possibly different constants. Okay, suppose they intersect at point T naught, Y naught. Then there are 2 equations. Or we had 1 in the last case, and now we have 2. And what varies here is C and K. But if we subtract, here it is. The conclusion is. What?
There's no difference between them.
Right, C is equal to K, which means that the two curves are over there are the same. So that picture on the right is impossible. So then that family of parabolas is what we want it to look like. It looks like a book, or I have a book here, maybe I have a picture here somewhere. Looks like pages of a book. Okay, so all right, so that was a simple situation in the sense that it was just a shift, and that's why the algebra was somewhat simple. Now we go to the kind of a perpendicular direction. So now if we look at our new differential equation, this one does not depend on t. Okay, so we had y prime of t, let me write it for you again, was g of t. Okay, so compare this, which we are finished with, and that. Okay, so as you can see, there is no explicitly t on the right. There's a y on the right, so abbreviated version is this. Okay, so this is the complicated one. So there, it cannot be solved by integration because, well, let me integrate for you. So if I try to integrate this, I have y prime dt here, and I have integral hy dt there. On the right, I still have a cancellation, so I still will have y, just like last time. Unfortunately, what's happened on the right? Integral h of y dt. Well, that's right, h does not depend on t. You cannot integrate h. You have to integrate hy, by the way, h of y, what is the, now look at the parentheses over here. What do we call this? Composition, right? So it's actually a composition of a function that we know h and the function that we do not know y. Okay, so in other words, the whole function is unknown. There is nothing to integrate, unfortunately, on the right. So this is the dead end. Okay, so what we have done is we turn a differential equation into an integral equation, but it does not, that does bring us closer to the solution. It does not. So we're not concerned with that right now, but let's just visualize what this is. So once again, slopes. But look at them now, the slopes change this way. The slopes change in the vertical direction, in the horizontal, there is no change. Okay, but the idea is still the same. You're supposed to cross somehow like this. You're supposed to follow these slopes as if they were tangent to your curve. And then you're supposed to draw a curve that continuously follow them. If we do it with the way we did it previously, it is incrementally, it is totally possible. As you consider, there is no issue whatsoever. You can build as many as you like, but we are now after continuous functions that change directions in a continuous manner, and there are continuously many slopes for us to worry about. Okay, so that's just to point out the difficulty. But here's one differential equation that has been solved. Okay, so and then doesn't matter how. This is the family of functions that we have produced. Exponential functions with variable coefficient, right? So it's not plus c anymore; it's times c. So this is my parameter. So once again, it is a single parameter family of functions, but the parameter enters the formula differently. So it's a plus c, or it is times c. Okay, so surely it's a very different thing. And then there's no shift, right? There's no shift, but rather instead of a shift, what's the relation between these curves? Addition shifts in the vertical direction.
It flips.
Multiplication, what?
Flips.
No, now if you look at -1 will flip.
Stretch it.
It stretches. That's right. It's stretching the vertical direction. So say f of x, f of t, and 2f of t. What's the difference? One is the second one stretching the vertical direction. So it's all these exponential functions. They're just stretched in the vertical direction. Okay. So well. So is it sufficient to conclude that this is the family right there? Okay, so once again, one parameter for each c, we have a different function. Okay, and then the question that we ask are the same. Is the plane fully covered by the curves? And secondly, do these curves intersect? The picture suggests exactly yes and yes. Okay, so let's demonstrate that it is indeed yes and yes. So how does it fully cover? Does it cover all the points on the plane? Once again, we start with t naught, y naught at such a point, and we need to find a curve for it. How do we find a curve? We need that constant c, the single thing that is variable here for it. Okay, so this is my formula. It passes for t naught, y naught, so I just put the subscript 0 there, and then once again I solve for c. So Whatever, why not? Because the exponential function is not never equal to zero, so we have safe to divide by et naught. And so then we solve for c very simply because the family was fairly simple, and we have then c is found if we have a point on the plane, just like the last picture that we had a point like this t naught y naught, and then so that's a given. And then what we did, we found the curve by finding finding C. Okay, so everything is covered. Okay, problem number one. Problem number two. What if there are two, or is it the same curve? So we already had experience just now when there was plus C and plus K, and we subtracted. So here instead of subtraction, what do we do? What algebra do we do with these two?
Division.
The divide, right? So we take these two, substitute first, and then, well, I actually subtract even though division, hold on. Is it better to subtract or divide? Why didn't I divide? You don't want to divide. Yes, subtract is still better because division will, there's also a possibility that you divide by zero. So even though if it's not zero, then everything works out. You have one, and one equal to c over k. So it works out perfectly well unless k is equal to zero. So in which case you have a little bit, you have to separate case, and each case you have to consider, not a big deal, but still. So it's just a way to alternatively to address it. So family of functions, so curves rather than functions, they're given. This one is definitely given implicitly. You recognize this curve. It's a circle, in other words, but because the radius, c is the radius, because it's allowed to vary, we don't have one, have a bunch of them, and it is a family of circles that cover the whole plane once again in the same manner, and so you can subject it to the same analysis and demonstrate that they do not intersect. Okay, so that's what the differential equations are. Ordinary difference equation, ordinary differential equation, just for the record, we put it forward, what it looks like, the difference function on the left, some function on the right, or after the limit, we have the derivative on the left, and we have the same function on the right. So one produces the other, and but we can go back if necessary, if we fail to make any progress with the with algebra pretty much. Okay, so all right, so oops, there you go. Right here. Okay, so ordinary refers to the fact that we have one independent variable. Okay, so no partial derivatives, which is a separate topic. We might have enough time to look into that. Okay, so say here, so that is the table. Lost some of the. Or DE. Yeah, so you can see that this, when you go from right to left, it's nothing but an abbreviation. Right, so I drop t in parentheses. If I remove t in parentheses, then things they just look simpler, and we want it to as compact as possible like this. Okay, so y is presumed to depend on t, and therefore it doesn't have to be repeated again. Okay, all right. So on the left, we now look carefully. On the left, we have a function of two variables, t and y. That's the more general case. And then on the right, it's a function of one variable. When we substitute, in other words, carry out the composition with y, then look at it on the right, it actually is a function of single variable t, because y depends on t and z depends on t, so together everything depends on t only. And so if that's the case, then there is a match. What I'm trying to say here is there is a match of functions. Both of them are functions of t and nothing else. So regardless of what it looks like on the right. On the right, it looks like the right hand side depends on y, but y is not a variable, it's a function. Okay, so here's an example. Once again, if the right hand side is a t squared plus y squared, I replace y with t squared. It's a substitution after all, so I end up with a function of a single variable, and that is the function that I work to match with when I am doing a substitution to verify a solution. Okay, so that could be that might come up Okay, so this is roughly what I was talking about. Once again, so sometimes because of the function of two variables, and if you haven't done enough calculus 3, function of two variables might be a bit too fresh, and to get you need to get used to it. But so that picture might help. Once again, function f is a function of two variables, t and y. The output is z. But if I make y a function of t, this is the step right here. So then the whole function is this. It is from t to z, and it is a function of one variable. Okay, so once again, algebra on the left and algebra at the top, and the diagram is just to illustrate the same thing as you have. Okay, so just to make sure with what's happening with this. Okay, so if once again, if the formula doesn't work, doesn't convince you, if the diagram might help too. This is the graphical interpretation. A function, the graphical function of two variables is what? It is what?
Three-dimensional.
It is, what I was going to say, it's a surface, right? In three dimension indeed. So this is a graphical function of the variables, top left. Okay, and then what happens, what does the substitution mean? We substitute that function at the bottom. Okay, so when you substitute one into the other, then you're going from t to y, and from y you go from t and y you go up to towards the graph, and that traces a curve on the surface, which in this particular case interpreted eventually as a function of single variables. This is, I guess, might illustrate the whole thing here. So you can see the function of two variables, that's the plane, and then the y, as it depends on t, is on the horizontal plane, and then the composition is going from t to the graph on the ty plane, then going up towards the surface, and then whatever elevation you discover gives you the composition, which goes from t to z. Okay, maybe more complicated than it deserves, because if you just look at the formula right here, that's all there is. Okay, so this is the substitution function of two variables, and then substitution carried out, and you have function. So it's called so this is a complication, that presence of t and y both on the left, especially. There's a simpler class of functions called autonomous differential equations that there is no t. Okay, so in other words, remember what differential equation is y prime is equal to f. Okay, so what that f, y prime is your velocity, and your velocity might depend on two things, on when and on where. Okay, so t is when, y is where. If it is only t when, you solve it by integration, and that's not our interest, it's too easy. So then typically it depends only on where. Like a flow, once again, we decide where you have a pipe, and each location we know how fast the flow is going, and we want to produce a path of an object floating in the pipe, okay, or canal. Okay, so but the flow does not change with time. That's the thing. So the flow is always stays the same. It varies in terms of location, but not in terms of time. Oh, so this is the challenge that I referred to a few times. There are infinitely many slopes to follow. Okay, so this is just three slopes. Okay, and you can easily draw a curve through them in a tangent manner. So it's crossing the vertical lines along these slopes, but then you have how many? You have more and more here. Each of these lines will produce the same thing, and that's why integration or differential equation is hard. It cannot be solved in any kind of a algorithmic way. So a book, layer cake, whatever you prefer that picture on the right that you see. What does it look like? So a bunch of curves, once again, tightly related to each other, never crossing, covering everything. There are no gaps. So that's what it is. The plane is fully covered by the curves don't intersect, and these correspond to two terms right here that are big, existence and uniqueness. Okay, every point on the plane has at least one solution curve passing through it, and uniqueness is every point on the plane has at most one solution curve passing through it. So it amounts to exactly one curve passing through it, even though it's not. Yeah, so this is still more precise yet not fully rigorous yet. So it's not fully rigorous yet because as you can see shortly that it's not entirely rigorous, especially part two. Okay, so let's have more examples. Okay, so existence and uniqueness. So existence and uniqueness came up in calculus in limits. Remember the uniqueness of limits, what it means? Well, the definition of the limit or derivative as a limit is indirect. So it's a limit is the limit is a number that satisfies certain property. If something is introduced in that manner, it means that there is a question: can you have two numbers satisfying the same property? Okay, and then you have to demonstrate that actually now it's not the case. You can have only one limit, which only after that you can actually speak of the limit rather than of a limit. Okay, so that's a similar thing. And also there's a possibility, and once again in theory of limits, is that there is no limit in the first place. So that's totally on topic here. It's possible not to have a limit. You have a sequence or a function, you ask what the limit is, and there is no limit. Same with derivatives. Function might not be differentiable. Why? The certain limit doesn't exist. Function is not integral because certain limit does not exist. If it does, then there's only one. So we have guaranteed uniqueness, but we do not have guaranteed existence for the limits. Okay.
That's fine.
Okay, so let's a quick look at the issues that we might worry about. Then the difference between equations, as this shows that you can speak of uniqueness and existence of solutions of equations, right? So for example, 3x plus 1 is equal to 0. 1 and 1, there is existence, there's always a solution, and there is also uniqueness, right? So linear equation always has only one solution, exactly one solution, with the exception of, well, there's an exception. So for example, 1 is equal to 0. Well, neither. Okay, so a quadratic equation. So that's linear equation. Easy to separate them. The ones that have exactly one solution, those that have none, possibly. Okay, and then well, actually 0 equal to 0 is the third possibility. So for linear equations, there are three main possibilities: one solution, no solution, and one infinitely many solutions. So there are only three possibilities. Quadratic equations, you can have once again 0, 1, or 2. So with differential equations, way more complicated because of this. Equations may have overlapping domains. Okay, so literally, so we will have those nice pictures, and they seem to be very self-explanatory. But is this a solution? So if I take, is this a solution? So a piece of the graph. Okay, so, and the answer is maybe. So we would probably should also put it on the list because at every point you differentiate, you plug into the equation, and everything is satisfied, even though the domain is small. So that's not how itself it precludes it from using. Okay, so once again, so this is simply differential equation that come from motion. Okay, when the velocity happens to be linearly, the first equation here linearly depends on time, then we integrate and we end up with our quadratic equation from, remember what it's called, I think it's called kinematic equations from high school, possibly. Looks familiar? Right, and the second one is just population growth once again. Okay, so these are the domains are negative infinity, infinity, but that's not always the case. In certain circumstances, what you might have an asymptote, in which case the domain is not everything. Okay, so for example, y prime is equal to 1 over t solved very easily by integration, but we know that at 0 it cannot cross 0. Okay, so the answer is logarithm, but really what the reality looks like, you have a bunch of equations on one side and on the other side. And so the domains on the left may be they could be, what's the largest domain on the left? It's negative infinity 0, right? On the right, that's the domain. On the right, the largest domain is 0 infinity. Okay, so then as you can see, there is no one way to approach it because of remember, one possibility is that the domain does not have to be negative infinity. Okay, so I'm just trying to justify why we are not allowed to just say one solution per point, because every smaller solution will still count, unfortunately. It's a bit inconvenient, but not too bad. So we have a look at this. Only interesting observation too is that for this particular differential equation, very simple one, but what's on the left and on the right are not linked with each other in any way. It's like two universes that there's a gap between them. So a solution on the left, that say blue one, does not have anything to do with the solution with the blue one on the right. So it's not one constant, it's two. Okay, so in other words, you can vary on the left independently for what you vary on the right, because once again, there is no link between them. So it's actually two parameter family of solutions. So two family of solutions, or better yet, two parameter family, better way to describe it. Okay, and why in that reflects the nature of the domain, which happens to have a gap. You can imagine if there, instead of having one cut, would you have two cuts? There will be three parameter family, once again, three different pieces, and then within each of which there's a separate family, and therefore they're the three parameter family. Okay, so once again, solution is when you substitute, you end up with an equation of two equal functions within the domain. As you can see here, we are now being careful, and we speak of the function defined on an interval. Okay, so a function does not exist unless its domain is provided. So that's especially important here because domains might vary, which you usually don't encounter when you do calculus. So the domain comes with the function, and then within that domain, only within that, we do differentiation, and the two functions have to match. It's called a strong solution, just in contrast to a weak solution, which we will take a look later. To remind you, this becomes very important. The functions are required to be differentiable. Otherwise, how do you differentiate? The left-hand side requires derivatives, so how do you make things equal to each other unless you finish your differentiation? Okay, so just to refresh your memory, the conditions of the hierarchy of functions. Okay, so differentiables are the best ones. They are slightly less restrictive continuous. Then there are integrable, and beyond that, there are non-integral functions. They're bad, especially, but nonetheless, continuous functions are pretty good. So so what's wrong with a motion described by a continuous non-differentiable function? To emphasize the point, right? To emphasize the point, why do we insist on differentiability and not on continuity? A motion that is continuous is all we ask for. Why do we want it to be differentiable? What does differentiability mean in the context of motion?
Because if it were to change its motion instantly, that would require.
Changing its direction, right? Instant change, it's not a jump. It's not teleportation, that would be discontinuity, but non-differentiability still has a problem because we change directions instantaneously, which is also bad. I mean, you can think, and so you want, when you speak of, say, object thrown in the air, planetary motion or anything like that, they never change. You don't want to assume that there's an instantaneous change in directions. But you can consider when, for example, how about a puck or anything, whatever hits the fence board, and then it kind of changes directions instantaneously, right? The simplest way to understand how a ball, or why do I pick a puck? Because it does not have a give, and so if it is a ball, then it will contract. Obviously, in that moment of time, you can speak, well, it turns around gradually. But if it is anything more rigid, maybe even a golf ball, they are very rigid, and so the almost instantaneous change of the shifts, they don't have any contraction abilities, so it's almost like instantaneous bounce up. So certain certain events such as this, we exclude it. If we insist on differentiability, then this is out. Okay, so anything rigid motion, rigid bounds is out entirely like this. Okay, so the way to deal with it, and that's the let's just quickly run through this alternative approach, and that's what we already saw. It's integrate. If you integrate, then the right hand side, the left hand side, we take our differential equation and integrate. The left hand side cancels out by the fundamental theorem of calculus. On the right, I have an integral. Okay, so if we look at it, that equation in red here, then it seems like the same as before. The changes, it doesn't look like huge, but you can tell what's the difference between this and that differential equation and integral equation. What's the difference? In the spirit of this discussion, does y have to be differentiable? There is no derivative anymore, right? So just as well, without derivative, what do we need from y? Well, we need to make sure that the right hand side is defined, so we need integrability on the right, and that can be accomplished by y being, for example, continuous, not differential necessarily. So it's called a weak solution. Okay, so we still require y to be continuous, but no point is being differentiated. That's what I would end up with an equation. We end up, so remember, continuous functions are all integrable. Okay, so which means that if f is continuous and y is continuous, then the function, whatever we have on the right will be continuous and therefore integrable. Okay, so it works out perfectly in that respect. And then you can plot it. So for example, this is let's carry out some of the computation this way. So on the right is my function f, which is not continuous, and therefore y cannot be differentiable. So within each of these squares, that indicates the slope, and you can see them. If you can see it's there, you can see can you see the slopes? So yeah, 45 degrees, 45 degrees. So the -1 down 45 degrees, -1 again. 1 is 45 degrees up, and 0 is up horizontal. Okay, so the function, my function is not continuous. Okay, so conditions change incrementally, which is not really, you can't have that in real life. For example, if it is maybe you should change it from one, maybe how about friction? Okay, so you move from one from a smooth to non-smooth instantaneously, and therefore the effect on your motion will be changed instantaneously, even though you still want continuous path. Okay, so as you can see, you cannot go from one square to the next. My solutions are made of these lines. But when you move to one to the next, you might have to change directions instantaneously, such as an example is here. Okay, that's not differentiable, but not unplausibly possible. So if you're going like this, and then it's like a grooves go this way, and then they go that way. You will feel the jerk, but you will turn like from you're going this way and then that way. So it's still a crude model, but then you don't have to deal with differentiability. So let me plot maybe one, say if I start this way, then I go horizontally, and then I go vertically, and then so 45 degrees, and then horizontally again, and horizontally again. So that's the solution for you. Okay. It's plausible. So here I plotted a bunch of them. So that's some weak solutions. So weak solutions here. Okay. So once again, there's no differentiability. You can change that the corners indicate non-differentiability. Okay, so all right, so they called piecewise linear, but the issues are the issue. So every strong solution is a weak solution. That's all good. So let me skip that. There is a problem that I wanted you to see right here, and that is what about uniqueness? It's not entirely obvious that you're going to have uniqueness. That's the problem with this approach, that uniqueness and existence is become an issue. So at the edges, that's the question here, at the edges, there might be intersection of these curves. And so uniqueness kind of goes away, unfortunately. So then the classical differential equations theory does deal with with strong solutions rather than weak solutions. Nonetheless, so it's interesting. And secondly, I want to throw an example at you from real life time. Taxes actually it involves integration of function that is piecewise. So these are tax rates. And if you need to know the tax bill, what you do, you integrate. Okay, the function is integral, but not differentiable. Okay, so it produces nonetheless meaningful answer. Okay, so I'll stop here. Dr. Smith, see you next time.